People, from the dawn of time, have enjoyed soccer. The traditions have changed throughout history. For example, mankind used heads instead of soccer.
Whoa there. This is physics, not history.
That's right. Today, we will instead be looking at the physics of the ball in three scenarios. When the ball is at rest, when it is rolling across the grass, and the instant of it being kicked into the air.
In this scenario, the soccer ball is at rest, sitting on the grass.
The two forces acting on the ball are force of gravity and natural force.
Since the ball isn't accelerating, there is zero net force, which means the forces on the ball must be balanced.
According to Newton's first law, the object will stay in constant motion.
The first law is about inertia, meaning that an object moves at a constant speed infinitely when there are no other outside forces acting upon it. The soccer ball is moving at a constant speed of 0 meters per second in all directions, making it at rest.
Now, we look at the soccer ball rolling across the grass. Man, what a beautiful sight that is.
Adam, let's get back to physics. You can stare later. There are three forces acting on the ball: force of gravity, natural force, and force of friction.
Inertia keeps it moving forward, but because of the friction from the grass, it will slow the ball down quite a bit, as dictated by Newton's second law.
There is, in fact, a net force in the y direction, causing the ball to decelerate to the right.
That's also called unbalanced forces. An example numerically is, say we have a frictional force of 100 newtons in a 30-kilogram ball.
That's a pretty heavy ball.
Anyways, in order to find acceleration, we need to use Newton's second law's equation. Net force equals mass times acceleration, which, if we were to break it down algebraically for this problem, is the force of friction minus the force of kick equals mass times acceleration. Or, in order to find acceleration and simplify it further, the force of friction minus the force of kick divided by mass equals acceleration. Now we can cancel the force of kick because it is no longer applicable to our problem, which leaves us with the force of friction divided by mass equals acceleration. So the answer would be 100 divided by 30, which equates to 3.33 meters per second squared. Super cool, right?
Yeah.
Alright, now moving on to the best part of soccer, the part that actually gets the game going.
Ah, yes, the revolutionary kick that occurs in the game. If we didn't have kicks, the game would never be in motion.
In this case, there is a diagonal force in the left direction, causing for us to need to find the x and y component of the force of kick.
The overall free body diagram looks like this, with the normal force being the same as the force of gravity, and an additional force going upward due to the x component of the force of kick. In the x direction, there is an x component of the force of kick going to the left, and in the force of friction going toward the right. Since the object is accelerating, the force of friction is smaller than the x component of the force of kick.
In Newton's third law, there is such a thing as third law pairs, and it refers to the foot and the ball in terms of free body diagrams. The force of the ball on the foot is equal to the force of the foot on the ball.
And now, to end this session.
Goal!